Bismillahirrahmanirrahim. Selamun Aleyküm ve Rahmetullah ve Berekatuhu. Okay. Now we are going to speak about sublinear, functional, and seminoles and Hambanach theorem. Hambanach is one of the most important theorem in functional analysis. Before speaking about the Hambanach theorem, we need some definition. Let X be a vector space and W be a subspace or linear subspace of X. So we have a linear, we have a vector space and a subspace of X like W. Let f of W be a linear function on W. So we define fw on W, not on all x. A linear function fx on x is extension of W if the restriction of f on W equal W, equal f of W. It means that if we choose W from capital W, then f of fx, f index x of W equals fw of W. So we say that f of x is the extension of f of W, or f of W is the restriction of f of x on W. Here we define the extension of a function on a vector space. Well, now if x is a norm space and W is a bounded, we write the extension f of x such that f of fx be bounded, and we have this equation. The norm of f of W as an operator norm equals the norm of fx. Theorem 4.19 section B showed that if W is dense in x, it means that W bar equals x, and Fw belongs to W prime, means Fw be a function on W, then Fw can be extended to by continuity to x. Hanbach theorem is a theorem that says we can extend Fw to Fx in more general condition, not just in this condition when W is dense in x. Another thing, exercise 5.1 shows that if M is a closed linear subspace of a Hilbert space H, and if M is a function of N, or if N is in N prime, then Fn can be extended to H. Another definition, let X be a real vector space, a sublinear functional, not linear functional, sublinear functional of X is a function like P from X to R, such that P of X plus Y is less than or equal P of X plus P of Y for all xy in X. B, P of alpha X equals alpha P of X, then X is in capital X and alpha is a real number, is a non-negative real number. For example, the absolute value of A plus B has the property A, and it has also the property B. Another example is the norm of x plus y. It has the property A that we call triangle inequality, and it has the property B too. There are some examples of sublinear functional, not linear function, sublinear function. For example, the norm of x is sublinear, the absolute value of f of x is sublinear, as I told you. So these are two examples of sublinear function. Another example for x to be r power 2, if we define if we define p of x1, x2 equals the absolute value of x1 plus x2, then p is sublinear. They are not linear, but this is a sub function. In this case, if P is a sublinear function on x, then we can prove that P of 0 equals 0 and minus P of minus x is less than or equal to P of x for all x in x. And minus P of y minus x is less than P of x minus P of y, and this is less than or equal to P of x minus y for all x and y in x. If P satisfies this equation, P of minus x equals P of x for all x, and then P of x must be non-negative or positive, non-negative. It means that P of x must be greater or greater than 0 or equal 0 for all x. And so we can write the absolute value of P of x minus P of y is less than or equal to P of x minus y. Another definition, let x be a real or complex vector space. A semi-norm, not norm, it is semi-norm on x is a real valued function p. It means that a function p from x to r, so it is real valued function p such that p satisfies these two properties. A, P of x plus y is less than or equals P of x plus P of y for all x and y in x. B, P of alpha x equals the absolute value of alpha P of x when x is in x and alpha is in L, or alpha is a scalar. With these properties, if we have another property such that Px equals 0, we conclude that x equals 0. X equals 0. If you have this additional property, P will be a norm. Here we see that, we also see that a semi-norm P is a norm if and only if P of x equals 0 implies x equals 0. So with this addition property, P will be a norm. But without this property, P is a semi-norm. Example, there are some examples here, but note that if P is a semi-norm of x, we have these properties. P of 0 equals 0 and P of minus x equals P of x, and P of x is non-negative for all x. And we have this inequality, the absolute value of P of x minus P of y is less than or equal to P of x minus y for all x and y in x. Now we can speak about Hahn-Banach theorem. Let x be a real vector space with a sublinear function P. So before studying Hahn-Banach theorem, we need to say that what is sublinear function, and we spoke about sublinear function. So x is a real vector space with a sublinear functional P defined on x, and suppose that W is a linear subspace. W is a linear subspace of x, and f of W is a linear function on W, such that for all W in capital W we have this inequality. F of W is less than or equal P of W. So we have a vector space W, a subspace, a vector space X, a subspace W, and a functional f of P on W, and a sublinear functional P, such that fW of W is less than or equal to P of W for all W capital W. Then fW has an extension fx on x, such that we have fx of x is less than or equal to P of x for all x in capital X. The aim of Hahn-Banach theorem is to extend a functional from a subspace to the main space, when we have this condition for a sublinear functional P. Lemma: if G is a linear functional on V, then there exists a unique real valued linear function gr on vr. vr means the vector space v on real valued function, real number, such that g of e equals grv, means the real part of g minus I g r iv for all v. And we can show that the norm of g equals the norm of gr. Another lemma: let X be a complex vector space and let P be a semi-norm on X. Here P is a semi-norm. Semi-norm is one of the examples of sublinear functional. So it is a special sublinear functional. It's a semi-norm. And suppose that W is a linear subspace of X and fw is a linear function on w. Satisfy this inequality, the absolute value of fw of w is less than or equal p of w for all w in capital W, and suppose that fwr be real functional on wr, obtained by applying the previous level. So fw can be extended to fx or on xr, such that we have this inequality. And fw has an extension fx on x, such that fx satisfies this inequality. Now we have Hanbarov theorem for complex vector space. Let X be a real or complex vector space and P be a seminorm on X, and suppose that W is a linear subspace of X such that Fw and Fw is a linear function on W, satisfying this inequality. Then Fw has an extension Fx on X such that we have this inequality for all X in X. This is a very important theorem in functional analysis, but the proof is not easy. Now we should wait until the internet come back. It has died now, so let me see. Okay, deteriorate came back. Oh no. Unfortunately, the internet is weak here, and sometimes it becomes dead. Okay. The previous theorem was Hambanov theorem in vector space, and there was no need that X be norm space. It must be just a vector space. Now there is another version of Hambanov theorem for normed space. So this is a version of Hambanov theorem for normed spaces. Before that, we need some lemma. Let X be a real vector space, and W a proper linear subspace. Proper means W can't be the whole X. It must be a real or proper subspace of X. And let P be a sublinear function on X and Fw a linear function on W, such that Fw of W is less than or equal to P of W for all W. And suppose that xz1 is a vector that is not in W. We define W1 as the span of Z plus W. It means the set of all alpha Z1 plus W for all alpha in R and W in capital W. Then there exists a KC1 in R such that the W of f of W1 from W to R satisfies this equation and this inequality. Fw1 of alpha Z1 plus W equals alpha KC1 plus Fw of W, and this is less than or equal P of alpha Z plus W for all alpha in R and W in capital W. We omit the proof. Now we are ready to speak about Hambanov theorem for normal space. Let X be a real or complex norm space and W a linear subspace of X such that for any Fw in W prime, means the dual of W, there exists a Fx in X prime, that is the extension of Fw such that the norm of Fx equals the norm of Fw. This is also an important theorem in functional analysis, but the proof is not so easy. Another theorem, after Humboldt theorem, we will have some results or conclusion from the Humboldt theorem. One of these results is this theorem. Suppose that X is a member of vector space X, satisfies this equation, delta equals the inf of W for norm of X minus W when delta is positive. Then there exists a function of f in X prime, the dual of X, such that the norm of f equals 1 and f of X equals delta, and f of W is 0 for all W in subspace W. Corollary, for any X in X, we have A, there exists f in X prime in the dual of X, such that the norm of f equals 1 and f of X equals norm of X. It isn't for all X, just for one X. We can find a function of f with these properties. B, the norm of X equals the sup of the set of absolute value of f of X, such that f is a functional with the norm 1. C, if y is a member of X with X not equal y, then there exists a function of f such that f of X is not equal f of y. It means that X prime separates the members of X. Corollary, if x1 to xn be in X and they are independent, linearly independent, so there exists functional f1 to fn in X prime such that fj of xk equals delta jk. Delta jk equals 1 when j equals k, and it is 0 when j and k are different. As I said, the above theorem says that X prime is separable. If X prime is separable, then so is X. It means that if X prime is separable, then X must be separable. Now some exercises. Now the version of general Humboldt theorem. Definition: I think it's a difficult definition. We omit it. And some examples and zone lemma. Zone lemma is also an important lemma, but it's not in functional analysis. It is in, for example, logic or set theory. I omit this lemma. Definition. In this definition, we are going to define Minkowski functional. What is the Minkowski functional? Let C be an open set in a real norm vector space X, such that 0 be in C. Then we define Minkowski functional PC of C by this equation. Fc of P equals, it is defined to be equal to infinite positive alpha when alpha minus 1 x be in C for all x. Now because C is open and 0 is in C, then the set on the right side means here the infimum of this set is non-empty and PC is well defined. Okay. Now based on this definition, we have the following results. I think we should wait until the internet come back again. Okay. So P of C, PC of X is the infimum of positive alpha for which alpha minus 1 x be in C. We call PC Minkowski functional on of C. Unfortunately, internet is weak here. The lemma 5.29. Let C and X be as the above definition. And in addition, let C be convex. Here in this definition, C is just an open set, but we don't say that C is convex. But here, this is a further property for C, that C be convex. Then PC is a sublinear function on X such that C equals all X for which PCX is less than 1 and there exists a constant C such that PC of X is less than or equal the C of C dot norm of X for all X. Another theorem that is an important theorem in functional analysis too. Here it calls separation theorem. Separation theorem is suppose that we have two subset, disjoint subset like A and B. A intersect B equals empty set, means they are disjoint. There is no member in common for A and B. So let's X be a real complex or complex normal space and AB be two disjoint and convex set of X. Then if A is open, there exists a function f and a real number gamma such that the real f of A is less than gamma less than real of f of B. Then A is capital A and B is capital B. And section B of this theorem says that if A is compact and B is closed, then there exists a function f such that and a positive number lambda delta such that the real of f of A is less than gamma minus delta less than gamma plus delta, and this is less than or equal the real of f of B. Then A is in capital A and B is in capital B. The proof is really difficult, and I will omit the proof. Okay, I think it's enough for today. I will send you the note of the lectures in WhatsApp. And we should decide about the time of midterm. I will send the last note, PDF of the last note of my lecture to you, and then we should decide about midterm. The time of the midterm. So I will take an exam of you, and the rest of the after midterm, the rest of the lessons will be for final exam. Please write to me in WhatsApp when is suitable for you for giving a midterm exam. Okay, I finished the lesson today. Any question? So please write to me through WhatsApp when is suitable for you. For example, next or next week, when you are ready for midterm midterm exam, and I told you how many of the lessons will be for midterm, and the rest of it will be for final exam. Okay? Any question? If there is no question, I finish the class. Goodbye.